citations can look right and still support the wrong claim. Use DeBERTa NLI in Python to test each RAG sentence against its source. This is the workflow you'll know how to run when we're done, which verifies generated claims against cited passages and flags unsupported ones. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. RAG systems give you answers that point to documents. That feels reassuring. But a citation by itself isn't proof. The model can stitch facts together, invent details, or pick the wrong sentence from a retrieved chunk. So, instead of trusting a citation blindly, we ask a single practical question. Does the cited sentence actually support the generated claim? What we want at the end is compact and actionable, a short list of claims labeled supported or unsupported, plus the exact evidence sentence used for that decision. That helps reviewers fix real errors instead of chasing every citation. For demos, you can get away with a few documents and low latency. In production, you scale the same steps with batching and better indexing. The flow stays the same. The pattern is simple and effective. Cheap filters first, deep semantics second. Use a fast lexical overlap to keep the easy wins cheap. Then run a DeBERTa MNLI model on the tricky pairs to decide entailment versus contradiction. Think of it as triage. Quick rules to remove noise. Then a semantic verifier for the risky cases. We'll code a small pipeline that takes a toy LLM reply with inline citation tags, splits that reply into individual claim records, computes lexical overlap against the cited passage, selects the best evidence sentence inside the source, and finally runs DeBERTa NLI only for the uncertain pairs. The result is a focused list of unsupported claims you can flag or log for human review. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need to parse an LLM answer and convert each bracketed citation into a structured claim record so later steps can read the claim and its source separately. This snippet turns a toy RAG answer into structured claim records keyed by citations. It keeps the retrieved chunks in the docs dictionary, so later checks can read each source quickly. The answer string mimics an LLM reply with inline bracketed IDs, and segments splits it into per claim lines. The loop searches each segment for a citation tag, and when found, trims the claim wording before appending a dictionary holding the normalized text and cite. Because only matching lines are stored, the claims list stays clean and ready for downstream scoring. The printed count confirms how many claims require verification. Next, we add a fast lexical check so we avoid calling the heavy model on claims that clearly match their citation. This example adds a quick lexical sanity check before we reach expensive models. Inside the loop, doc text pulls the cited source content. Then doc terms and claim terms build lowercase token sets for an overlap calculation. The ratio line measures how much of the claim vocabulary is genuinely present in the citation, guarding against mismatched sources. Each result is stored with the original claim in claim support, so we can reuse both the text and the numeric score later. If we tightened the overlap threshold in future steps, more claims would fall through to deeper checks. The average overlap printout shows the overall coverage quality so far. Lexical overlap helps, but misses paraphrases. So we find the single sentence inside the cited document that most closely matches the claim wording as the best candidate evidence. This code pairs every claim with the sentence that most closely reflects it inside the cited document. It grabs doc text through the cite mapping, splits it into trimmed sentences, and stores the claim wording in claim text for reuse. Sequence Matcher scores each candidate sentence against the claim, letting Max surface the best supporting evidence, even when the wording is lightly paraphrased. The resulting dictionary list, evidence spans, preserves the original claim reference and the chosen sentence for traceability. If sources contained denser paragraphs, adding more punctuation delimiters would improve the candidate pool. The printed character count confirms we captured a substantive evidence snippet. With a candidate sentence selected, we build the NLI input queue. Only include pairs whose lexical overlap was low enough to justify semantic inference. This snippet prepares a verification queue that feeds the eventual NLI call. The list comprehension builds pending pairs entries that bundle each claim text, its chosen evidence sentence, and a Boolean needs NLI, based on the earlier overlap score. A second comprehension extracts lightweight payloads containing premise and hypothesis strings that Hugging Face Transformers expects for DeBERTa inference. Because we only emit payloads when overlap falls below 0.6, the NLI stage stays focused on risky claims instead of wasting cycles on obvious matches. Lowering that cutoff would shrink the queue, while raising it would increase recall at the cost of more model invocations. The print summary reveals how many claims still need semantic verification. Finally, we run DeBERTa MNLI on the pending pairs, interpret entailment labels, and count unsupported claims for reporting. This example runs the DeBERTa MNLI pipeline, so only truly unsupported claims bubble up. The model name constant keeps the Hugging Face identifier handy, and the pipeline call materializes a reusable text classification model instance. When NLI inputs is non-empty, NLI outputs collects batched entailment predictions, and checked iter hands out each result in order. Otherwise, the iterator stays empty. Inside the loop, every claim either consumes a fresh DeBERTa verdict or falls back to an assumed entailment, updating unsupported count whenever the label differs from entailment or the confidence drops below 0.5. Tightening that confidence cutoff would catch subtler doubts, while relaxing it would reduce false alarms. The final tally reports how many claims failed semantic verification. In a real system, you map these steps to your retrieval layer and to batched model inference, so latency and cost are manageable. The same pipeline works whether your corpus is a dozen documents or 1,000, but you scale the NLI stage with batching and careful thresholds. Quick recap. This pipeline checks each generated sentence directly against the cited passage and surfaces the specific evidence that supports or contradicts it. Use it when you need precise, claim-level trust signals for RAG outputs. One caveat: NLI models still make mistakes on subtle or highly technical claims, so keep a human review loop for the riskiest items. Next step: experiment with the overlap threshold and the DeBERTa confidence cutoff to balance cost and recall for your corpus. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.